So let's start looking at what we did last class. Okay, can everybody please calm down? No more talking, please. So last class we looked at a couple of new concepts. One of the new elements we looked at was what was called the mutual inductor. You must already have seen this in some form as a transformer, right? But we were doing it in a more, I guess, in a more basic way. So the idea is very simple. Okay, so you have encountered an inductor before where it was a single coil. Okay, the current and voltage relationships between the current through the inductor was related to the voltage across the inductor in a specific manner. Okay, through the self-inductance L, right? And you can take a second coil, okay, and its voltage and current relationships can also be defined. Now, as it so happens, if you start bringing these two inductors spatially close by to each other, what will happen is the flux from one inductor will cut the other inductor, okay, which means the flux will be linked. Okay, then what happens is the voltage across one inductor will be related not only to its own current but also the current through the other conductor also, the other inductor also. Okay, so this relationship is expressed using these sets of equations. Okay, these two sets of equations. So V1 was originally just L di1 by dt. Okay, now there will be a second term which is plus M di2 by dt. Okay, so this is the new term that has been introduced. Similarly, V2, okay, will have a dependence on I1 through the same M. Okay, and I told you we'll hit this property later. It's called reciprocity. Okay, and so you can, using these two sets of equations, okay, you can describe the relationship between the voltages and currents between these two coupled inductors. Okay. I also pointed out that once you choose the voltage and current directions for one coil, there is an ambiguity about how you choose the voltage and current directions for the second coil. Okay, because you could choose, as shown in this figure, you could choose the V2 and I2 in the opposite directions. As far as that inductance itself goes, it is self-consistent. Remember, we have already shown that if you actually have an element V, okay, and you have a current I, right? Now you could take this as minus V in the opposite direction, minus I in the opposite direction, and so on. Okay. The important thing to note is that this is just a representation of the element. This is just a symbolic representation. I could have chosen my current and voltage variables in this direction also. That is the point. These are just variables, representative directions you are choosing. Okay? These are just representative directions you are choosing for the currents and voltages. What will happen if the actual current is not in that direction? Let us say you chose a direction looking upwards, but the actual current through the element is, let's say, 5 amperes flowing downwards. What will happen? The answer which you, when you analyze the circuit and figure out your answer, I will happen to be minus 5 amperes, right? Which tells you that the current is actually flowing in the opposite direction. Again, that is the whole point. These are basically symbols standing in for the actual element. Okay, and you are choosing certain representative directions. You can choose any direction you want. Okay, as long as you are self-consistent for that particular element, and everywhere for all analysis you choose it in the same direction, your solution will be correct. Okay, now suppose for the second inductor you choose it in the opposite direction. What will happen is the sign for the dependence on the other current will of course change. Okay, instead of being L di1 by dt plus M di2 by dt, it will now happen to be minus M di2 by dt. Okay, so that means that we need to come up with a convention, a symbolic convention, to show, okay, which one it should be, which sign convention makes sense. Okay, and that is what we encountered as the dot point convention. Okay, so anytime you see a pair of coupled inductors, you will see something like this. Okay, you will see a couple of dots placed close to the inductors to show you, first of all, to show you two things. Number one, those two inductors are coupled, right? Number two, it shows you the direction in which they are coupled, because the dot point convention says that currents entering dot points, okay, in the symbol for the coupled inductor produces currents entering dot points produce additive fluxes. What does additive flux mean? It means that they tend to reinforce each other, okay, which means that M is positive. The mutual inductance is positive. They are positively coupled, okay. If you happen to choose, again, you are still free, even with these dot points, you are free to choose any voltage and current directions, okay. If you end up having a negative current, for example, okay, that will show up in your equations. The only difference is, if you happen to choose currents entering dot points, if somebody tells you the coupling factor is something, or M is some number, you can assume that M to be a positive number, okay. If your variable happens to be I1 entering one dot point, I2 leaving the other dot point, you have to assume that M is negative. Is that clear? The important thing is to be self-consistent, okay. Now M can also be represented in terms of what is called the coupling factor K, okay. M is nothing but K root L1 L2, okay. K is also called the coupling coefficient, and you will find that K is, the magnitude of K is less than or equal to 1. Somebody asked me after class why this magnitude needs to be less than or equal to 1. Any ideas? Yes. Okay. Absolutely. That's right. So if you have two linked coils, yes, what we said is this mutual effect happens because the flux from one coil, right, due to the current in one coil, cuts the other coil, right. The best case you can have is when the flux, all the flux from one coil cuts the other one, and vice versa, right, and that will happen in a case where K equals 1. If you have partial coupling, okay, only part of the flux cuts the other conductor, okay, then you will have K less than 1. So if you are actually trying to create a transformer, for example, where you want this coupling to be as tight as possible, okay, you will build it in a specific physical spatial configuration to try to make sure that the flux cuts it as much as possible. Is that clear? Okay. And note that I have given the general case with the two inductors being different. If you have two identical inductors and perfectly coupled inductors, the mutual inductance will be the same as the self-inductance in terms of value. Yes. You don't have to stand. Yeah.
Sir, like in the dot point convention, for the let's say the first one you drew there.
Okay.
Current entering the dot points will produce additive fluxes.
Correct. If I assume I1 and I2 like this, okay, I will write down the equations with a positive M.
So what if you choose the second one, sir? There it contradicts, right?
No, it doesn't. If I choose I1 and I2 like this, I will write down the equations. See, as of now, I don't know V1, I1, V2, I2. Correct? Let's assume, because these are the variables I'm interested in. The voltages and currents. In fact, that is one of the things we are going to see in today's class. If you take any electrical circuit or any electrical network, the quantities of interest are the voltages and currents. Okay? If I have some n elements inside a network, okay, I am interested in 2n quantities, n voltages and n currents. I want to know exactly what the voltage across every element is. I want to know what the current through every element is. Once I know that, I can say I know the network perfectly. Right? I know everything there is to know about the network. Because remember, if you had gone, remember electrostatics, you were interested in the field and the charge and so on. Here, as far as the circuit is concerned, you know the voltages and currents, you can say you know everything about the network. Okay? You know everything about the circuit, because everything else are, everything, all other quantities are derived quantities from this. Okay? If you want to know the power dissipated, you want to know the energy dissipated and so on, you can calculate it based on the voltages and currents. Is that clear? That's number one. Number two, suppose you don't know these. You can assume these directions. Then what are you going to do? You're going to write down the equations. Okay? You're going to write down the equations. When you write down the equation, since you have assumed in this direction, you will write it down as you will write it down in this form. Okay, you will assume, you will write it down with a positive plus M di2 by dt and so on. Okay, if you had assumed it in the opposite direction, you would use minus M. Is that clear?
So that would mean in this case we have to assume the voltage is in the reverse direction. I mean, one of the voltages is in the reverse direction.
Okay, that comes. So what you are asking me is, should you assume this voltage in this direction? Should you be assuming V2 in this direction? Right? That brings us back to our passive sign convention. Right? Since we have decided to go with passive sign convention, we are going to go, if inside any element, okay, we are going to assume that the current flows from the higher voltage terminal to the lower voltage terminal. Okay, because we have also established that an inductor is a passive element, because though power may not be dissipated, okay, you have to use energy to actually set up the magnetic field. Is that okay? Any other questions? Okay, actually one more question which one of you had after class was, why inside an inductor? Maybe I can. Let's say this was I and this was V. Okay, I have an inductor. So one of you wanted to know why the sign of the voltage is this way and not the other way. Okay, for example, I'll take the simplest example. Maybe I have an inductor like this. I just take a current carrying conductor and create a loop, right? And I have current entering here and leaving here. Okay, why should the voltage direction be here? Any ideas? What is the voltage current relationship in an inductor? The voltage is L di by dt, correct? Okay, so first of all, just passing a DC current doesn't do anything, right? If I just have a fixed current, okay, of so many amperes, 1 ampere, 2 amperes, it doesn't do anything inside an inductor. I need a time varying current. Okay, the next point is, the minute I have a time varying current, let us take a linearly time varying current. Okay, so dV by dt can be, let's say, some positive constant number or some negative constant number. If it's negative, the current is decreasing. Okay, let us take the simpler case where the current is, so dV by dt is positive. What happens? In which direction do you expect the voltage to be developed and why? So let us say, I'm going to say, sorry, di by dt is what I meant. I'm telling you di by dt is positive. I want to find out the direction of voltage which makes sense for us. How will you figure it out? Electric flux. Magnetic flux. Okay. There is no electric flux. Well, yeah, there is no electric flux. Magnetic flux. Okay. The voltage develops across the coil, not the current. Is that what you want to say? What law is that? Lenz's law. What does Lenz's law say? Okay, one of you please raise your hand and tell me what it says. Yes, you. What is your name? Prashant. So Prashant, what is Lenz's law? It will always oppose the effect causing it. Could you please add a little bit more detail to Lenz? Lenz will be turning over in his grave, okay? So let us pay some respect to him and state it properly.
The voltage induced will be such that it will oppose the change in current.
Change in current causing that voltage. Okay. So now I have told you current is entering here, leaving here. It is positive. So in which direction should voltage be developed and why? I think if you remember, we had done the power and energy calculations for the capacitor. Okay, I just gave you the final answer for an inductor. I hope all of you did this. If you did it, you will see why it needs to be in this direction. Because when you have a positive di by dt, okay, you are basically putting in energy into the inductor to set up the magnetic field. That is half Li squared. I hope all of you have confirmed that for yourself. Assuming that the inductor is completely discharged. There is no current. Okay, I'm going to call it discharge, but there is no current through the inductor at first. I of 0 is 0. Okay, to set up the magnetic field, you have to put in an energy half Li squared. Okay, so you are basically putting in energy from outside. What does that tell you about this element? What does that tell you about the direction V and I? We have seen that power is positive, okay, when you have this current entering from the positive terminal and coming out of the negative terminal, right? Inside the element it flows from plus to minus, okay, for the voltage. So in other words, the voltage will be developed in this way because it will create an energy barrier for you need to push in energy, okay, to actually create that magnetic field. That's why the voltage will be developed in this direction. Is that okay? Okay. So apart from that, we looked at the passive sign convention. Again, P of t instantaneous power is V of t times I of t. Okay. This is the power dissipated inside the element. I use the word dissipated here because it's the easiest thing to do with respect to a, you all know about the resistor. Okay. The power is V squared by R or I squared R, definitely greater than 0. Okay. As long as V and I are greater than 0. So the resistor is definitely passive. We notice that a capacitor is, okay, the power is some CV dV by dt. Okay. It doesn't tell you much because dV by dt can be positive or negative, even though V may be positive. Okay. So you need to look at the energy, and what we pointed out was if the capacitor is originally discharged, you actually need to put in electrical energy inside the capacitor for you to be able to use it later, and that is half CV squared. Okay. Now the same thing holds for the inductor also. It has stores an energy half Li squared. So both capacitors and inductors are also passive elements. The difference between capacitors and inductors and resistors is this point of power being dissipated. In the case of a resistor, the power is dissipated typically in the form of heat energy. In the case of an inductor or a capacitor, the energy is only stored. This half Li squared or half CV squared, okay, can be reused, okay, by as in the electrical form, okay, at a later time. Is that okay? At a later time, this energy can be reused. So it only stores energy. So during a certain period of time, okay, when you are trying to set up the magnetic field, if you have a positive, in this case, if you have a positive di by dt, okay, what happens is there is energy stored in the magnetic field. The inductor absorbs electrical energy from the rest of the network to set up the magnetic field and stores the energy in that form. It can also give it back to the rest of the circuit, okay, and get discharged. Okay, that is the point, and same holds true for the capacitor. Any questions? Okay, so I'll modify this slightly. Or absorbed is what I modify this slightly, because dissipated is true for a resistor, not necessarily true for inductor and capacitor. Okay. Now what about an active element? An active element is one where electrical energy is generated. You already know about these kinds of electrical elements. Voltage sources, current sources are examples of active elements. Okay, and we looked at this particular to show that a voltage source or a current source can actually absorb or can generate or absorb power. Okay, that can happen. I'm sure all of you know about, you do have rechargeable batteries, right? So of course energy can be pushed into a battery to be stored in the chemical form. Okay, we don't care about the conversion to chemical as far as this course is concerned, but you can have energy being pushed into a voltage source or a current source. It depends on the direction of the voltages and currents. Okay, now I gave this as a homework. I asked you to do this, do the case of the energy to find out whether a mutual inductance is passive or active. How many of you have not done this homework? Oh good, this is the first class I have seen where everybody has done the homework. Raise your hands please, properly. Okay, so everybody else has done this? Okay, what happened? Why haven't you people done it? What's your name? Aman Verma. So Aman, tell me why didn't you do this homework? It would have taken you exactly 2 minutes to do this. Okay, in the future I'm going to start, if I see this happening multiple times, I'm going to start cutting marks from your tutorial marks. Okay, for people who are not doing these kinds of simple 2-minute homeworks. Okay, this I just want to make sure you do all of this. Okay, those of you who have done this. So, quick question before we move on. I wrote the power as V1 I1 plus V2 I2. Why is it V1 I1 plus V2 I2? We have seen for a single element, that is Vi, that is easy to say. Why is it V1 I1 plus V2 I2 here? The assumption is that, okay, so assumption is there is some energy being put from outside into this magnetic field again. At least that is a reasonable assumption. Okay, so I have not shown this here, but you could actually put in a voltage source or a current source to drive this. Okay, so there is some energy being put in, and into this inductor, right, you have V2 I2, and in this inductor you have V1 I1. Right, that is why I wrote it as V1 I1 plus V2 I2. And your gut feeling should tell you that this particular element is passive. Okay, because it's created from two inductors, and you know that energy is stored in the magnetic field, right, even for a coupled inductor. You can extend the case of the inductor self-inductance to this also. Except when you actually work it out, okay, what expression did you get for the energy? Half L1 I1 squared plus half L2 I2 squared plus, this is what you must have got. Okay, plus half M, plus M I1 I2. Okay, you won't get any 2 and all. This is right. This expression is right. Now your gut feeling tells you that this should be passive, right? So what do you expect this energy to be? Should be greater than 0 to set up this energy inside the inductor. Okay, now if you use this condition, right, this makes sense, right? This makes perfect physical sense. You need to put in energy. Just a pair of coupled inductors doesn't have energy by itself. Okay. Now if you use this inequality to figure out what M is, right, or rather you define M as some K root L1 L2. We have already seen this before. If you write down this equation, okay, you will get a certain relationship for K. Okay, you will understand why the magnitude of K should be less than or equal to 1 from this. Okay, if you actually put it inside this. So you can look at this from an energy point of view. Okay, this should tell you why the magnitude of K should be less than or equal to 1. From a physical point of view, from the flux also it makes sense. From the energy also it makes sense. Okay, you put these two together, this will tell you that magnitude of K should be less than or equal to 1. Okay? Okay, fine. So after this, we'll move on to some quick stuff, series parallel connections. I think all of you know about this. We will just rush through it, right? So if I tell you, this is what is called a parallel connection. Okay. This is what is called a series connection. Okay. How do you distinguish between a series connection and a parallel connection? If you have a parallel connection, the voltage across the two elements is the same. Okay. The currents are different. Okay, so you have the same voltage V across both. In the case of a series connection, you have the same current I through both the elements. Okay. What else do you know about this? If you have a current I1 entering this, Okay, so maybe I'll call this I3 here. I have I1, I2. Okay, you also know that you know V1 equal to V2. You also know that I3 equals I1 plus I2. This is just a very simple, trivial application of KCL at either of these two nodes. Okay. Similarly here, okay, you can apply KVL. So if you have V1, V2, okay, and you have an overall voltage V, this V equals V1 plus V2. Okay, so you have a series connection, the overall voltage is the sum of the voltages. Okay, you have a parallel connection, the overall current is the sum of the two currents. Okay, I think it should also be obvious to you that the current coming out here is also I3. Okay, so this is all very basic stuff. So I have two resistors R1 and R2. Okay, what is the equivalent resistance? R1 plus R2. You already know this, right? How do you prove it? Of course, you write down the voltage and current relationships, right? What you are interested in is the overall V and the overall I, right? You write down the previous relationships for series elements, you will find out that the overall resistance is R1 plus R2. Similarly, you have R1, R2, okay? So the equivalent resistance is, so the better way to do this is the inverse of the R equivalent is 1 by R1 plus 1 by R2. Okay, and similarly if you have a third element, fourth element in parallel, you can just extend this further. Okay, if you have elements in parallel, the conductances, the overall conductance is the sum of the individual conductances. Remember, the conductance I defined as 1 over R, okay, the first or second class. So this is G1 here, whereas here this is R, R1, R2 plus so on. How many ever elements you have in series or parallel, you can write down these relationships. I have two inductances in series and two inductances in parallel. What is the effective inductance? L1 plus L2. Okay, here the effective inductance, the inverse of the effective inductance, okay, will be 1 over, so 1 over L equivalent will be 1 over L1 plus 1 over L2 plus so on. Okay, so for the inductance the same thing holds. I have two capacitances in series. What is the equivalent capacitance? Okay, in the case of the capacitance, it's slightly different. 1 by C equivalent is 1 over C1 plus 1 over C2 for a series connection. Okay. And for a parallel connection, it is the sum of the capacitances. Note that just for the capacitance alone, it's slightly different. Okay. What other elements do we know? Resistor, capacitor, inductor, voltage sources. I have two voltage sources V1 and V2. Okay. I want to replace this with a single voltage source V. Can I do that? I can do that. Okay. What is the value of the single voltage source? V1 plus V2. Okay. What if the polarity of this voltage source was reversed? It will be V1 minus V2. Okay? What about this case? It's not possible. Why is that? Exactly. Of course, you can see very clearly that KVL is not satisfied around this loop containing these two voltage sources. Okay, so you cannot make this connection. Okay, you cannot take two ideal sources and put them in parallel with each other, because one of them is going to try to assert a voltage difference of V1, the other is going to try to assert a voltage difference of V2. Unless V1 equal to V2. Of course, if the two voltage values are identical, you can put them in parallel. In that case, what is the equivalent voltage source? That is V1 equal to V2, the same voltage. What about current sources? Can I do this? I can't do this because KCL will be violated at the intermediate node. Okay. Unless I1 equal to I2. And in that particular case, if I1 was equal to I2, what is the value of this? It will be just the same I. Okay. What is this? What is the value of I? I1 plus I2. Okay, value of I is I1 plus I2. So these are ways to simply, simplify your electrical circuit or network. Okay, to make your analysis easier. For simple cases, you can do this very easily. Okay. What we are going to try to do is try to find out a systematic way of doing this for more complex networks. So let us say, can I make this connection? I can, right? 5 volts, 1 ohm, you can figure out what this network is. Okay. Can I make this connection? This is my network. It's a trivial network, but can I make this connection? What is this? This is a voltage source. Okay. So this is possible. I take a voltage source and I hold it like this, right, making no connections to it. Is that allowed? Of course it is, right? All you are saying is there is no current through the voltage source, but it still holds the same potential difference across it. Can I do this? What is this? This is a wire. Can I do this? No, I can't. Why not? Because KVL is not satisfied, right? This goes back, this is the trivial case of the previous one where I had V1 and V2. Can I do this? I have a current source, 5 amp current source. I put a 1 ohm across it. Who said no? Of course this is possible, right? You can easily figure out that you have a 5 volt voltage across the current source, which is perfectly fine. Okay. Can I do this? Of course not, right? You can't do this because KCL will be violated. Okay. This is perfectly okay. So if you want to store a current source, okay, an ideal current source, you will have to short circuit its terminals. Okay, it is not delivering any power very clearly. All it is doing is maintaining a current of 5 amperes through that wire. The wire is ideal, we assume it's ideal, no resistance, nothing. There is no power being dissipated very clearly. The voltage across the current source is 0 volts. Is that clear? Okay. Okay, fine. So that is, we just ran through some quick ways to do this. Actually, let us try a couple more. Can I do this? Yes or no? Yes. What is the voltage across the capacitor? 2 volts. Right? What is the current through the capacitor? How will you figure out the current through the capacitor? In steady state, it is 0. I equal to 0 in steady state. Right? If you wait for a long time, the capacitor gets charged. Right? Okay. What is this? Less than 4 seconds. Where do you get that 4-second number? Are you doing something different from what we are doing? This one. So tell me, why do you have to wait for 4 seconds?
I was saying
Less than 1 second. Why do you have to wait for 1 second? For it to charge. Why 1 second? Where do you get that 1 second number from? That's what I'm curious about. Any idea? Okay, we have not reached this point yet. We are going to look at these kinds of circuits later. But any idea how long this circuit will take to charge? Let us assume that the capacitor has no voltage across it and you are connecting it like this. 0. Why? It will be instantaneous, right? The charging will be instantaneous because you don't have any resistances in the circuit. We assume ideal wires. KVL has to be satisfied at every, right? KVL has to be satisfied at every instant, right? KVL and KCL, as far as we are concerned, are inviolable. Okay, so as soon as you turn this on, KVL has to be satisfied. Okay, so the voltage across the capacitor is 2 volts immediately. Okay, if you had some other element, some other resistance, for example, this will no longer be true. Now, before we move on, I just want to do this. Can I make this connection? No. Who said no and why not? Anytime in this class you say yes or no, you have to justify it. Why can't you make this connection? Yes. Okay, what is the, so when you decide whether to make connections or not, how do you decide whether you can make certain connections or not? Let us go back to this guy, right? You told me this was wrong. How did you decide that this was wrong? You applied either KCL or KVL, right? And along with that you made a certain, there is one more third assumption that you make. Not assumption, there is a third, piece of information that is given to you, which is the information about the element itself, what kind of element it is. Because if I just given you a resistor, whatever element it is, you can apply KVL, KCL, right? But the type of element gives you some additional information. Okay, it gives you some additional information and you are going to use that also. In this particular case, what is the additional information? This is an ideal current source, and the property of an ideal current source is that it is going to pump a current of 5 amperes in the direction shown, irrespective of what the rest of the network is. Okay, that is the definition of an ideal current source, and you can do this for an, so that is the property of an ideal current source. Okay, irrespective of the voltage across it. Similarly, for the voltage also you did the same thing, right? So whenever somebody gives you a network and asks, can you make this connection or not, what do you have to do? You apply KVL, you apply KCL, along with that the properties of the element, and see if it makes sense or not. So tell me, what is the property of a current source? Current is going to be constant, independent of the voltage. What is the property of a capacitor? It stores charge. But as far as we are concerned, yes, stores charge is a very general property of capacitors. In our particular case, what are we interested in? Voltage and current, right? We are interested in the voltage current characteristic of the capacitor, we know that the current through the capacitor is C dV by dt, right? Can you use those two and figure out what will happen, whether this is possible or not? Okay, rises to infinity, okay, that's right. But can you say something more about it instead of just saying it rises to infinity? Let us say initially this was discharged, the capacitor was discharged, and suddenly I make this connection. What will happen? Of course not. It won't explode. Definitely not. What will happen? Okay, you know the properties of the elements. What is the property of the current source? It has a current I equals 1 amp in this direction. What is this current then? 1 ampere. So this is I2 equals 1 ampere. So you already know the current through the capacitor. The only variable to find out is the voltage. Okay, so I'll call that V2, which is the same as V1 in this case. So this is what you are interested in finding. Correct? Using KVL, KCL. You've already used KCL to figure out that the current through the capacitor is 1 ampere. So how will you figure out V2? This is the characteristic of the capacitor. Okay, there is nothing to write for the current source because it's ideal. Irrespective of V2, it is going to hold a current I. And that is how you are able to write this equation. What is I2? What is the capacitance? Now can you tell me what V2 is? V2 is T. Assuming the capacitor is initially discharged. So what is the characteristic of what does the voltage look like? So if I draw V2 as a function of time, what will it look like? It's a straight line with a slope of 1. Okay, so 1 volt per second in our case. Right? Is this connection allowed? Of course it's allowed. What you are saying is you are passing a constant current through a capacitor and charging it linearly. Right? Why would it explode? Right? You see the voltage, as a function of time, the voltage will increase linearly, that's all. Now, yes, at some point of time it may explode when you cross the physical limits of the capacitor. But of course, as soon as you connect it, this will work fine till it reaches that limit. Okay? You can of course control the slope also using the voltage or using the capacitance or the current. That also you know. Okay? Okay, so let us stop here.